Homework Hotline, what is your emergency?
Hello everyone and welcome to the Homework Hotline.
We're here live every Tuesday and Wednesday from 4:30 to 5:30 p.m. We want to help you with your questions.
Yeah, and if you call us, we can interact with you and walk you through any of the problems that you call in. Calling is really the best way to get your question answered. Our number, if you want to call in, is 720-424-1666.
So we have a few ways you can watch us live. Actually, a lot of ways. Comcast, so many ways. Comcast Channel 22, Prism TV, Channel 8007, YouTube Live at Denver TPS TV, Facebook Live at EG Homework, or live stream at livestream.com. Search for DPS TV 22.
So we're here to help you with math and science. I'm Sam, and I can help you with science. Over here we have Becca. She can help you with math. Nate, who's normally here to help you with math, is off today. I teach at the Contemporary Learning Academy, and then Becca teaches over at Emily Griffith High School. And our two schools sponsor the show.
Though we prefer to get your phone calls, we know calling isn't always the easiest thing for you, so we have someone monitoring our social media. Why don't you tell us a little bit about yourself?
My name's Kylie. I'm a senior at University of Colorado Denver, and I'm an intern here at DPS TV and monitoring the social board today for you guys.
Awesome. Do you do the trivia question as well?
I do that as well, and I can give that to you right now if you'd like.
Awesome.
So our trivia question today is, who were the first people to use algebra?
Looks like the incorrect question was up on the screen. The real question is what you mentioned. Would you repeat that one more time for us?
The one I just said? Okay.
Mm-hmm. There we go.
Who were the first people to use algebra?
I like this question, of course. I do. It is right up my alley. All right, well, if you do have an answer to that trivia question or even just a guess for it, feel free to call us at the phone number that Sam gave you earlier. You could also send in your answer via social media, and Kylie can answer or, I guess, relay it to us that you knew what you were talking about algebra.
I wish.
But let's also give you our other contact information, how you can send it via social media. The phone number is right there. That'll stay on your screen the whole length of the show. But you can also get to us via social media on Facebook or Twitter at EG Homework. You can text your questions to us at 970-680-3771. And you can email us at homework@emilygriffith.edu. So all of those options. We've got plenty of options today.
That's right.
So we'll go back to Kylie, and we'll start by answering some of our questions that have been left for us on social media.
All right. I'll just go ahead with the first one.
Sure.
Reactants, products, and catalysts. Why is a catalyst not considered a reactant or a product in a chemical reaction?
Yeah, definitely. Let me pull up an image here that kind of describes what a catalyst does. Okay. So in chemistry, we often talk about reactants and products. And reactants and products are a way of describing the things that go into a chemical reaction and then what comes out of a chemical reaction. And this is one of those cases where just thinking about the words themselves, really thinking about what they mean, and those words meaning in other places can give you a hint as to which is which. So product is probably the most obvious, right? If a product is something that is produced, right, you would assume that that's sort of the end goal of something. In a chemical reaction, the products are what are produced. The reactants are then the things that would go in to the chemical reaction. So let's see, like an example of a chemical reaction might be you mix hydrochloric acid, HCl, with sodium hydroxide. When you mix those two things together, those are the reactants. So you've got them separately in bottles, throw them into the same test tube, let's say, and watch them react. And then on the other side, you would get salt, sodium chloride, and water, H2O. And those would be your products. So you have your reactants and your products. Catalysts are not reactants and products because catalysts really just sort of, in a sense, they help a reaction along. They're not They're not little living things, but their existence, if they are around a chemical reaction, it will allow that reaction to happen faster. If we jump to my screen, I have a picture. I should probably blow it up a little bit. But this is sort of a classic graph that's shown in chemistry classes, and it sort of shows an uncatalyzed reaction in blue and a catalyzed reaction in red. And then on the left side, on the y-axis, you have the energy required to make this reaction happen. And then on the right, or on the y-axis, x-axis, excuse me, you have time from left to right. So as time passes, how the reaction goes. And what this is essentially saying is, if you have an uncatalyzed reaction, if you have a reaction without a catalyst, without a chemical that's going to help, the energy needed is much higher. And what this is showing is that you have to reach this level of energy before the reaction can take place. If you don't reach this level of energy described here by the peak, you cannot get the chemical reaction to happen. Sort of the downslope here represents the reaction actually occurring. This line right here is actually the activation energy line. The catalyzed reaction, shown in red, you can see requires much less activation energy. And that's because the catalyst is there helping along. And it can be something like the fact that a catalyst might have a charge. So that charge might be helping in some way. The shape of the catalyst, so if the catalyst is a complex molecule, like all of us inside of our bodies have chemicals which act as catalysts, biocatalysts, to reactions. And those are very complex proteins typically. And their shape is really what allows reactions to happen more quickly. They, in some ways, can grab onto the reactants that they need and put them together to make products. That's an oversimplification, and again, I don't want you to get the sense that chemicals are living creatures putting things together. It's because of their charges and their shapes that these things happen naturally, but it's almost as if they have that kind of agency. So anyways, really long-winded way of saying, reactants go into a reaction. They're kind of like the ingredients in your recipe. Product is sort of like the thing that comes out, whatever you were baking. And then catalyst is just a chemical that can help that happen with less energy.
That was something that was really difficult for me to understand in high school until I saw an animation of a catalyst. I was like, what do you mean it helps it? How does it help?
And actually looking at animations are really great, but it is such a strange concept in a way. And it really is, when you talk about, I really think that it sounds like these chemicals have their own agency. Like a chemical's thinking, oh, I'm going to help this chemical get together with this chemical. But it's really just by nature of, again, its charge, its shape, how it's going to interact with other molecules, and essentially bring two closer together. And then in the case of biomolecules, it really does, the animations, like one molecule will come into the catalyst and the other molecule will come into it, and then it'll change shape and actually put them together. Yeah. Worth checking out those animations if you're trying to get an understanding of this.
Yeah, absolutely. That's what did it for me. It clicked then when I saw it. But very interesting.
I'll pull one up for later.
That stuff.
But I'll let you do a math problem. I don't want to deprive you of any.
Oh, understood. Got to share the love, right? All right, Kylie, what do we have in regards to math?
All right, let's go right to the next one. Let's see. Write a recursive routine to generate the sequence of numbers, then use your routine to find the 10th term of the sequence.
Okay.
So the sequence goes as, there's four numbers, -3, 6, -12, 24, and then ...
Okay, and we need to find the 10th term.
Correct.
Okay, so recursion, I guess my best way of explaining recursion would be is something is repeatedly happening to numbers, and it's a sequence, and we use the previous number to find the next one, is the big idea of recursion. On my screen is the sequence, and what was asked of us was to find the 10th term. We have to find that. And so let's talk about that at first. This would be considered the first term, and the second term, and so on. And one of the most confusing things, and I kind of wish I had Nathan to back me up here with this, one of the most confusing things with recursion is the notation. The concept's really easy. You just need to figure out the pattern, and then we need to repeat the pattern. But the notation, meaning like the way that it's written, is what's the most confusing when it comes to recursion. So what we use, sometimes you might see it used as U sub n, or sometimes you might see it as A sub n. As well, we'll go U sub n just because that's what I'm used to using, but you might see it a lot of different ways. But really, what this is referring to is the nth term. So we could call this -3, for example, we could call it U sub 1 because it's the first term. And then 6 would be considered U sub 2 because it's the second term. And that number, Nathan has mentioned this before, this little number on the bottom, it's just referring to which term we're talking about. So if we're finding the 10th term, we'll kind of go back to that over here, we're going to be looking for U sub 10. That's what we want to know. So we use this U sub n to speak generally, to write the recursive routine, as was mentioned in the question. So to write our routine, we need two things. We need to identify what our first term is. So we'll say U sub 1 is equal to -3. This gives the reader or whoever is following the recursive routine, it gives them a starting point. They know that, okay, I'm starting at -3, and then I'm going to do this to the number, and I'll get something else. So then possibly the next thing that we need to do is think about what is the pattern. What are we doing to get from number to number in this sequence? Usually you're either multiplying or adding something. And when I say multiplying, I also mean dividing, because multiplying and dividing kind of go together, same with adding and subtracting. So we want to think about what we're multiplying or what we're adding. You might notice that here, -3 to 6, there'd be two options. We could either be multiplying by -2, or we could be adding 9. So what we want to see is which one of these would hold true for our pattern. So if I added 9 to 6, I wouldn't get -12. So it's probably not that. That's not really our pattern. So we'll try the multiplying by -2. And if I do 6 times -2, it does give me -12. So let's just make sure that this holds true the whole way through. And it does. So that is our pattern. Once we find our pattern, or know what we're multiplying by, this is called a constant multiplier. It kind of makes sense. It's what we're multiplying by consistently to find our next numbers. So we know that to find every number in this sequence, we're just going to have to multiply the previous one by -2. So the way that we would write that, and here's what I mean when I say the notation is tricky sometimes, is the way we would write that is we'd say U sub n. So to find any term, we're going to have to take -2 times the term before that. And let me kind of explain that notation of what I just wrote up there. Hang on, let me find my mouse here. When I say U sub n minus 1, let's think about this. So if my U sub n, let's say I was talking about U sub 5, then that would mean U sub n minus 1 would be U sub 5 minus 1, which is equal to U sub 4. And this is the term before 5. So n minus 1, or U sub n minus 1, is the way to algebraically express the term before n, whatever's one less than n. So for example, using that kind of idea, that if I were to find U sub 10, which is what we're looking for, I would have to take -2 times U sub n minus 1, 10 minus 1. Or in other words, U sub 9. I'd need to take -2 times my 9th term. Well, in order to get my 9th term, I'm going to have to take -2 times my 8th term, and so on. So what we do with recursion, and this is one reason maybe why recursion is sometimes not always the most useful way about it, is we have to just consistently calculate our terms all the way up to our 10th term. So it's almost just like continuing a pattern. Right here that I just finished up here, this is the recursive routine that was asked of us. Recursive routine. It's kind of just like an equation for us. And then we're just going to continue our pattern to find our 10th term. So I'm going to do this in maybe a table just to be organized about it. So let's say I had my first term. We said that was -3. We know our second term, that's going to be 6. Our third term was -12. Fourth term was 24. And then we're going to continue this. So we're going to do our fifth term. It's going to be 24 times -2, which is -48. Our sixth term would be -48 times 2, which is going to be +96, or sorry, times -2. And then seventh, we're just continuing, 92 negative. And then eighth term, ninth term, 10th term. So let's give us some space for this. So we have, we'll say 380, 4. And then doubling it, my goodness. My brain, whenever I am on the spot sometimes, does not work. I'm sure.
That's tough. You're going to do a part where it's a little bit tougher.
Just doubling things. Oh my gosh. Okay, so just quicker this way sometimes as well. So we'll say -768. So there's our 9th term. And then we have to take that times -2 again. And we end up getting positive 1,536.
That's a process.
So it is a process, and that's why I don't love recursion, honestly. I like regular equations because we can just plug in 10 and get our answer. Mm-hmm. There is a process on your calculator where you can kind of repeatedly hit that button over and over and over and over again. But that, again, what if we were finding our 100th term or our 1,000th term or something like that? Makes it not a great process for larger numbers or larger calculations. Right. So we would just say U sub 10, or our 10th term, is 1,536.
Wow.
Recursion's all about patterns. And again, trickiest part about it, I think, is the notation, the way to write it. Mm-hmm. So hopefully that helps. Let me know if you have other questions about recursion. I just know that that's kind of a nightmare topic for students sometimes.
Definitely.
All right. So I think we are going to do more questions.
Yep.
Yeah.
All right.
Let's do it.
Let's see. Geometry pick. This looks like a science one. I saw a video of solid sodium reacting with water. It catches fire. Are there other metals that have similar reactions with water, and is that reflected in their organization on the periodic table?
Yeah, it definitely is. I will talk about that in just a moment. But let me just really quickly run through
the
enzyme
animation. Yeah.
So if we could jump to my screen really fast. I just wanted to show really quickly. So, okay, so this is an enzyme.
This is so much like the
They're
I
all
can tell
like
already.
pretty much the same. This could be the one. The McGraw-Hill stuff has been there for a long time. Anyways, this is all you can just find out on the internet. It's easy to find. But an enzyme is a molecule that your body produces to help a reaction happen more quickly. So this is a catalyst to a reaction. It's a biocatalyst, so we call it an enzyme. Okay, so here's an enzyme, and then that area, a little indented area, is called the active site. That's where the reactants of the biochemical reaction will land. So you can see their shapes match up like puzzle pieces. They're called the substrate in biology or biochemistry. That's not something in strict chemistry. If you're just talking about mixing chemicals, reactants and you use a catalyst, the substrate terminology does not apply. But in biology, it does. So the substrates, which are essentially the reactants, come in. They sort of like nest into the enzyme, and then they become the product that your body wants to create, whatever that might be. So in our animation here, this is sort of happening slowly. Oh, wow. Very exciting. And then the product can then detach from the enzyme. And the enzyme can go on and continue to do this. And if we back up and kind of just look at the substrates, if I can get the thing, the substrates really, they, from their appearance, you can tell they would sort of lock together naturally. And it is true that the reaction of the substrates coming together would happen anyway, but the enzyme lowers the activation energy and allows this to happen more quickly. So that's one way to think about an enzyme. And I'll just mention also really quickly that you don't have to be combining things for this to be an enzyme. You can have a larger molecule that latches onto an enzyme, and the enzyme then breaks that up. You would still call the larger molecule the reactant, and the things that come out at the end the products. It's always the stuff that goes in that you start with that's the reactant, and the stuff that comes out, which is the product. So anyways, little wrap up of the last question. So then this new question is about sodium reacting with water. So let me pull up our handy dandy periodic table. Cool, so if we could jump to the screen really quickly. So this is ptable.com. It's a really great periodic table website that I have mentioned before on this show. So the molecules that we're, or the elements that we're interested in here for these types of reactions are going to be our alkali metals, and to some degree our alkaline earth metals, but much more strongly our alkali metals. So the periodic table is organized in such a way that as you move from left to right on the periodic table, and this is general, the rules get more complicated as you get more in depth with it, but we'll keep it simple. So as you move from the left to the right, sort of skipping this middle area here, you add an electron to the outer orbital or electron cloud that element has. So if you haven't taken chemistry before, the basic notion is that atoms have a nucleus formed of protons and neutrons, and around the nucleus, these little tiny particles called electrons are sort of flying around in these what are called electron clouds, which just describe the space that they float around and kind of zip around in. Anyways, the outermost cloud is important in thinking about chemistry, and the periodic table allows us to know in the outer orbital how many electrons do you have. So starting from the left, you can count lithium has 1 electron in its outer orbital, beryllium has 2, boron has 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and then neon 8. And 8 is a full orbital. And again, I'm glossing over some finer details, but generally this is true. Okay, so back to the question. Alkali metals, so all alkali metals are in this left-hand column, meaning they all have just a single electron in their outer electron cloud or outer orbital. They would really like to get rid of that extra electron for reasons of stability. When they have the electron, they're charged neutrally. But when they lose the electron, they become positively charged, and they would really like to lose that electron. And if you take a block of, let's say lithium, or what is it, sodium in this case, you take a block of sodium, and sodium is a metal. It's not a metal like we tend to think of metal like iron, but you could get a block of sodium. You'd have to order it specialty, and it's very dangerous because it could even react with oxygen. And if you were like to throw it into water, it really does look like it sets the water on fire. And effectively what's happening is all of the sodium gets in the water, and water is polar, and the sodium will just instantly give up that electron that it has. Polar means that the water has a positive and a negative side. So the electrons will be given up, and the sodium will become positive. And sodium is very positive at that point, and it would really like to latch onto something else. And so it will actually break up water. And so water, which is H2O, will be broken up, and H will be ripped off of the water molecule. It'll combine with another H to form hydrogen gas, and will gas off. And the OH that's left over, a compound called hydroxide, will latch onto whatever the alkali metal was, in this case sodium. So you end up with a compound called sodium hydroxide, or you end up with sodium and hydroxide ions in the solution. But it's essentially the energy of that really positive alkali metal ripping apart the water molecule and joining the hydroxide piece that releases so much energy that it is a fire, essentially, is what you get. You get the burning of water, which is what this is. And so really this is reflected by the organization on the periodic table. The most reactive is lithium. Lithium is the least electronegative element. But then as you move down the scale, all of these guys, sodium, potassium, rubidium, cesium, and francium, would all react really strongly with water.
That's interesting.
Yeah, the videos are really great too. You should check out YouTube. Look up alkali metal in water. It's It's great fun. Usually it's like some people standing around a lake like, oh my gosh, you ready? You ready, guys? And then it really is a pretty amazing explosion. But
Why is it so much fun to make explosions?
Right.
it's just kind of
so
funny.
much fun.
So much of YouTube, like YouTube science videos, are just one kind of explosion or another.
Reactions are fun. They just are.
They can
Explosive
be.
ones.
All right, well, we're going to take a little break. When we come back, we'll answer some more of your questions, so get those sent in. We'll see you soon.
Feel better? Being a single parent is hard, it's time consuming,
Somebody left their toy in here.
it's scary.
Fright can often turn into inspiration.
If it weren't for her, this wouldn't be what it is today. I'm gonna make a cake.
That sweet girl inspired her mother into a sweet career.
I'm gonna decorate a cake for Valentine's Day.
Jordan Higgs
Okay.
owns the Cakery by Jordan.
I will just keep on adding red. Home-based businesses are really growing. And just start layering it on here. It started in 2012 when a friend needed a cake.
Her business was learn as you go.
Well, I had been winging it until I started to go to Emily Griffith and really refine my skills. I knew that I wanted to work for myself, so I chose Emily Griffith because I'd heard a lot about their cake decorating and their baking program.
A decision that's paying off.
My skill and my career have just really expanded greatly since then. I've been afforded a lot more opportunities than I would have otherwise if I hadn't started going there, which is something I'm grateful for because now I can call myself a professional.
Those skills create delicious creations.
I get to make pretty things or fun things. I get to add to people's events. I get to create people's wildest dream pieces. I take pride in being able to bring those imaginations in your head to life. Strawberry vanilla cake.
Her success inspired by this little life.
That is beautiful. Delilah Rose, my 4-year-old daughter.
A little girl motivating improvement in her mother.
It was so important for me to be able to still better myself because she's always looking. There's no way to give up when there's two little eyes watching you.
How could you not be inspired to overcome challenges when a face like this looks up at you?
I'm very grateful for the hardships. They brought me to Emily Griffith. They brought me to my own business where I live comfortably off of what I do.
Welcome back. Hopefully you enjoyed that. You can actually take cake decorating at Emily Griffith Technical College. So look into it if that's one of the things that you're interested in. We've got a lot of cool things.
It is a pretty cool school.
It is. I'm a little biased, but it is really cool.
I'm not biased, and I think it's cool. So
You heard it? Not from me. All right, Kylie, more questions?
Yeah, I guess I'll start off with the math. Oh, geez.
Oh, only Nate was here, but you can handle this one.
Oh, my.
That's basic.
All right,
basic
let me
GM.
find it on the...
I don't even know if I can tell you what it is. In the diagram below, 3 lines intersect at N, which is right here in the middle. The measure of angle GNF is 60 degrees, and the measure of angle MNL is 47 degrees. What is the measure of angle HNK?
Okay, let me see if I can get the image onto the
Yeah,
notebook,
that would
because that's
be-
going to make things... Oh, come on. Why won't you work? There we go. I have no
Nice
idea
job,
what I
Becca.
did, but I
I think you
figured
have
it
to
out.
paste it as an image. They give you like different ways you can paste, but you did it right.
Well, I did it.
You got it.
Woohoo! All right. So, geometry, I have to admit this to start off with, it's not my favorite. And typically I field these questions to Nathan because it's not my favorite. Historically has never been my favorite. However, we'll work through it. I'm sure we can do this. So, we are finding H and K. So I'm going to highlight the one that we are finding. So H and K would be this particular angle. So that's what we want to do. Now, typically with geometry, and since I'm a struggler of the geometry, one of the first things that I do is I label everything that I know. And I try to think of all of the things that I know, all the facts that I know of this whole thing. So it says that GNF is 60 degrees. So GNF is going to follow the points GNF, that would be this angle here, and it's going to be 60 degrees. Also says M and L is 47 degrees, so we'll label this one. M and L is 47 degrees. Now, I'm trying to, I know that these angles are congruent. I don't know the postulate for it. Okay, how about this? So if, I can explain it. Okay, got it. Got it.
Yeah, you got it.
So I could not think of what it was called. And that's part of my issue with geometry is I'm just kind of, I know what's congruent, and I just don't know how to.
I would have a really hard time with the vocabulary. I can't
Explain
remember
it.
what those angles are called.
So what I am doing here is I am looking at this figure here, and I took out that line, that GL line. So I'm looking at M, that's N, and this is F. Okay. Does that make sense? Actually, let's do this. I have a better idea. Sorry. Don't you know I love geometry? Okay. I'm going to do these two instead. It'll get the same point across and it'll be more productive. So here I have G and L. So does this make sense? I just took out the line HM from that so we can just see the figure without so much mess. This right here, so angle, those are corresponding angles, vocabulary.
Okay.
And corresponding angles in geometry, or in just whatever, corresponding angles are always congruent, meaning they have the same measurement. So given that idea that corresponding angles are congruent, then we can use that to help us figure out some stuff. So my angle is going from N to K, right there, to here. Those are my two congruent angles that I highlighted over there. And so we would say, oops, sorry, I did that wrong. This is why I love it. All right, so from N to K, this right here, and this right here, those are corresponding angles. And so we can assume that the angle LNK, this other one over here, is 60 degrees because they're corresponding angles. Now I can maybe start putting some things together. I also know that if I have, so this angle here, all three of these need to add up to give me 180 degrees, just because they are supplementary angles, vocab. So since they need to add up to give me 180 degrees, I'm going to take my 47 degrees plus 60 degrees, and maybe we can call that angle X for right now, and we'll say angle X, and that's supposed to equal 180 degrees. So adding these together, we get 107 degrees, and then solving for X, we end up getting, 63 degrees. So then we can say this angle X is going to be 63 degrees. So far I only used two postulates or theorems, I don't even know. But corresponding angles, the ones across from each other, we know that they're equivalent. And then we also know that supplementary angles always add up to give you 180 degrees. We then can make a couple more assumptions here. We can assume 47 degrees. These two angles, GHN and MNL, those are also congruent because they are corresponding angles. So 47 degrees, 63. All right, so, sorry, give me 1 second. Hang on 1 second. 73 here. My bad, I'm sorry. So 73 here. Got to add up to 180. I should be checking my work like Nathan. All right, so 73 degrees. Anyways, all right, so our angles, our corresponding angles across from each other are congruent, and so that would be considered 47 degrees. And then same with this angle and the angle over here. we could say that that's also 73 degrees. Now, we also know, so maybe a way to check our work as well, and if you're me, you should definitely do that. Our angles all together should all add up to give us 360 degrees because it's a full circle. So we will double check that. And we do. We get 360 degrees. So back to the original question, it asked, what is the measure of h and k? I tend to find all of the angles that I can because it's not usually straightforward in that you can directly find h and k. You usually have to find some other things and fill in some other clues before you find it. So I tend to find all of mine, and then I'll go back and answer my question, which h and k, that is the yellow angle that I highlighted to begin with, would be 73 degrees. So,
Nicely done.
other than my little math errors, but I did remember the vocabulary. Got that. I gotta practice, man. Gotta practice.
Oh, you're good. You're good. I mean, Nate is great with the vocabulary, but you had the concept.
Truth.
Can I make a request for the next one?
Sure, go ahead.
Can I get the Northern Lights?
I was going right for
I
that.
should have just let you do it. Should have just let you do it.
Because I thought, all right, when learning about the Aurora, oh gosh, I don't know how to pronounce that, Borealis, also known as Northern Lights, I found out they are caused in part by the Earth's magnetic field and atmosphere. But what is the interaction that actually causes visible light?
Yeah. Do you know what Aurora Borealis means? It means the Northern Lights. So Aurora means
I was going to
light,
guess that,
and
actually.
then Borealis means northern, or boreal, right? You sometimes hear about boreal forests, northern forests. But yeah, anyways, sorry. So the Aurora Borealis is fascinating, and probably everybody has seen a picture of the Northern Lights in their lifetime. Hopefully everybody has. They're gorgeous. I've never actually seen them.
I went to Alaska in the summer, and people asked me,
Did you get to see
did
them?
you get to see the Northern Lights?
And did you?
No, I went in the summer.
Oh, you went? Sure.
No sunset even.
And that really is the thing, right? So you need the dark to be able to see the Northern Lights because they're just dimmer than the light of the sun. Anyways, so the way that this happens is Earth does have a magnetic field. Let's just really quickly talk about that and why. If we could jump to my screen really quickly. So Earth has a magnetic field that generates because of its plates and its mantle and its core. And essentially the idea is that the Earth is composed of a lot of nickel and iron inside of itself. Out here on the surface, it's composed of lots of silica and other things, but it's very iron and nickel rich in the core of the Earth. And iron and nickel are two metals, or they're elements that are metals that are able to generate magnetism and electricity. And essentially what you have is, I've got, I think, another image I tried to pull up here. So this is an image of convection current. So the core of the Earth is the hottest, densest part of the Earth, and as it heats the stuff around it, the mantle is liquid or approaching liquid, and so it has currents inside of it, and the currents of this like molten iron and nickel mixture, as they move and sort of swim through the mantle in these, as described by these little circles with arrows here, they move continents apart and bring them together, which is super relevant for geology. But in this case, what we're interested in is that they actually move electrons around as they're doing this. The individual iron and nickel atoms will actually pull and push electrons around inside the core, and it generates some fairly consistent fields, electromagnetic fields. And so then what you get is the sun's rays, as they shine down on Earth or toward Earth, there are electrons contained in those rays, and they get pulled by the pole, the northern pole of the Earth. And so you can see here in the diagram we have electrons and ions being pulled, negatively charged ions being pulled toward the northern pole of the Earth. And so as these electrons and ions come toward the northern pole of the Earth, they start knocking into the gases in our atmosphere. And the most common gases in our atmosphere, so the most common gas in our atmosphere is not oxygen, but nitrogen. Nitrogen is like 78% of the atmosphere, and it's in the form of N2, and it's not it's kind of inert, doesn't really do anything. And there's about 20-something% oxygen. And then there's smaller amounts of things like carbon dioxide and water vapor. But nitrogen, when it gets knocked into by these electrons and these ions, what will happen is those electrons will excite, sort of add energy to the gas molecules as they're floating around. And the electrons of those gas molecules will get excited and will do what we call jumping energy levels. And so they'll get excited and they'll move further away from the nucleus of the atom, and they'll have more energy. And then they'll lose that energy and they'll jump back to that original position. And in that loss of energy, the electron will give off a photon, which is an energy packet seen as light. So, and this is a really cool phenomenon that happens not just from the Northern Lights, but I used to be a park ranger in Carlsbad Caverns in New Mexico, and we had the cave is formed out of limestone in Carlsbad, and there was this one particular statue where we used to do this thing. It looked kind of like a crocodile, and we had gigantic lights. It's a cave, it's very dark in there. So we had these gigantic flashlights we carried around as rangers. And if you shined the flashlight into the eye of the alligator, I mean, you could have done this to any piece of rock in the cave. But if you did it to the eye of the alligator, the photons emitted from the beam from the flashlight would actually excite the electrons of the limestone atoms. And they would jump energy levels. And then if you pulled your flashlight away, those electrons would jump back to their original energy levels, give off photons themselves, and that would give off this greenish light. And so the eye of this rock alligator would glow green in the dark. It was really a cool little thing. But it's essentially the same process. And then, there's different colors in the Northern Lights, and that is because of the different chemicals. So nitrogen, I think, is seen as, what was it? Nitrogen is seen as red, and oxygen is seen as green, I believe. I can't remember. I looked it up. But in any case, that's the gist of why this happens. It's that exciting of electrons to a higher energy state, and that can happen in lots of different ways. And then when those electrons jump back to their normal energy states, they give off a photon, and that is what we see as the Aurora Borealis.
That is so cool.
Yeah, it's really interesting.
That was really cool.
Interesting stuff.
Wow. I like it.
Nice.
Okay, I guess math again.
All right.
Do we have any? Oh.
There was, okay. It's a word problem.
Oh, I read this one. I like it.
Yeah? Okay.
It's fun.
Do you want me to read it? Okay. Let's see. So one night the king couldn't sleep, so he went down into the royal kitchen where he found a bowl full of mangoes. Being hungry, he took 1/6 the mangoes. Later that same night, the queen was hungry and couldn't sleep. She too found the mangoes and took 1/5 of what the king had left. Still later, the first prince awoke, went to the kitchen and ate 1/4 of the remaining mangoes. And even later, his brother, the second prince, ate 1/3 of what was then left. Finally, the third prince ate 1/2 of what was left, leaving only 3 mangoes for the servants. How many mangoes were originally in the bowl?
I love this
Yeah,
question.
that's a great question.
It is a really fun question.
Working backwards, I think I've almost got it.
Yeah.
That's a good way to put it.
So you could solve this algebraically. You could. It would be pretty convenient to do it. However, I would just like to work backwards in this scenario, starting with this third prince here. And what we had at the very end is we had 3 mangoes at the very end. So we had 3 mangoes. There's my mango. Mango. They're kind of green, right? They're green. Green.
Yeah, I think when they're
green and
when
like
they're
pink
unripe,
and like orange and
they kind of ripen up.
maybe I'll get like some little shading. Nope, that didn't work.
That was
Never
good.
mind.
That looks like a great mango. Well, it's fine. We know what they are.
All right, so mangoes. So our 3 mangoes. So he ate half of what was left, and this is what was left. So prince number 3, he must have eaten 3 of them. So before prince number 3 got to the bowl of mangoes, there were 6 of them. Does that make sense so far?
Oh yeah, so much sense.
Okay, so we took care of the third prince. Like, so before he got to it, there were 6 of them. Then let's think about what happened before that. So this is the brother, the second prince. He ate a third of what was left. So a third of something is going to be 6. So if he ate a third, he ate a third of what was left. We don't know what was left. And then when he ate a third of that, we're left with 6. So we can maybe think of this as, how could I explain this? We have 1 part, 2 parts, and then here's what he ate. So this is 2/3. Mm-hmm. So if he ate a third, there was 2/3 left. So what we're saying is that what is in front of us, these mangoes, 6 mangoes, is 2/3. So if we break it into 2 pieces, that's 2/3. We need another one to make the 3/3.
Yeah, I think the packeting is the way to do it. I think that'll allow you to do it the whole way.
Yeah. So this is what, this is the 1/3 of what that second prince ate. So now we had 9 mangoes before the second prince got there. And then it says later, and I'm going to erase my groupings just because that might change. Later, the first prince awoke. So this happened before, second guy, so this is first guy. He went to the kitchen and he ate a 4th, which means that what we have here is 3/4 of the mangoes that were there before the first prince came. So this is 3/4. So that means if this is 3/4, so here's our 3, 1, 2, 3 groups. He ate those, or sorry, that's what was left. He must have eaten the same amount. He must have eaten 3 as well. So this is the 1/4 that he ate. So that's, at this point, that's the first prince. Mm-hmm. Now we have 2 more people that ate. Now again, I'm going to erase my groupings just because that might change as we go backwards. So let's say, so before the first prince awoke, the queen got to these mangoes, and she ate 1/5 of what was left. So that means whatever she ate, so whatever this is, that's 1/5. So that must mean the rest of it is 4/5. So again, because it's 4/5, I can put this into groups of 4. 1, 2, 3, 4. And then she ate the 1/5, so it had to be an equal part. So she must have eaten another 3 mangoes as well. So this is the 1/5 that she ate. All right, so we got the queen. We just have to get back to where the king, what did the king do? So we took care of queen, she's done. And then king, he ate 1/6 of the mangoes. So similar idea, if he ate 1/6, that must mean that this, what's in front of us, is 5/6. And my groupings actually show there's 5, we need 6 of them. So there were 3 more mangoes there, 2, 3. So we're thinking all together, 1, 2, 3, 4, 5, 6, that there were 18 mangoes all together. And one thing that we could do is we could go run this problem again forwards and make sure that it actually makes sense since we worked backwards to get to our answer. So let's start from this. Let's say king, he ate 1/6 of the mangoes. So here are our 6 equal groups. He ate 1/6, so he ate 1 group out of 6. And then queen, she ate 1/5 of what was left. So now we're in 5 groups. She ate 1 of those groups. So she ate those. First prince, he ate 1/4 of what was left. So into 4 groups, and we're already in that. He ate 1 of those 4 groups. Second prince, his brother, ate 1/3. So he ate 1 out of the 3 groups. So he ate 3 mangoes. And then finally, the third prince ate half of what was left, which is 1 out of 2. And then it says leaving only 3 mangoes for the servants. So interestingly enough, I like this problem for 2 reasons. One, just because of, I don't know, it's a very rich problem with fractions. And then 2, it's really interesting. It shows you a lot about fractions that even though they all ate the same fraction amount, they actually all only ate 3 mangoes.
Right. Yeah,
So-
it's funny, like you look at the third prince, sounds a little greedy, because he ate half. King seems so, prudent.
Right, he
eating
only ate a six.
But really, everybody in the family just eats 3 mangoes. And if they only have 1 servant, they left the same number of mangoes for that servant.
That's so true. I
And they
didn't
were
even
really
think of that.
equitable.
That's actually pretty
Each
fair.
of them just came up and took 3.
So they might not be that greedy at all. They might be a very nice.
And you could always divide anything equally, right? If you had 7 people, you could just essentially be like, first person gets 1/7 of what's there, next person gets 1/6 of what's there, next person 1/5, right?
I like it.
One way to do it.
It's a great problem. It's a good one. So 18 mangoes. Okay, well, let's go get more questions.
More
All right.
questions.
More questions.
So let's see, where did that go? Oh, I'll just do basic anatomy. I know the nervous system runs through our whole bodies, but exactly what part of that is considered the central nervous system?
Oh, that'd be the brain and the spinal cord.
Yeah.
Done, your turn. Just kidding. Just kidding. I'm just joking. I'll talk about it for a minute.
Wow. Not fair.
So the central nervous system, let me pull up a diagram of it, and we'll just talk a little about what the nervous system does and why we call it the nervous system, etc., etc., etc. If Nate were here, I might have done that. But, okay, we'll pull up this really generic-looking human. Just white male, average age. Okay, if we could jump to my screen really quickly, please. So this is just a really simple diagram that shows the brain and the spinal cord. Spinal cord is just like a really thick braiding of nerves that comes off of the brain and acts as sort of the central wire that all other neurons are connected to. And I think it is apt to describe nerves like wires. They're obviously not exactly like wires that we use in machines, but they perform very similarly. And really the way that our nerves work is through electricity. Our bodies in general function through electricity, but our nerves in particular through what's called action potential. Essentially, neurons can send messages by pushing positively charged ions across a medium, and then as those ions move back across the medium, they'll send electrons moving, and that can essentially create an electrical pulse. In any case, the remainder of the nervous system extends through the body. You can kind of see from this diagram all these different little fibrils coming off of the spinal cord, and those would, of course, extend to all different parts of the body, giving us sensations like the sense of touch and temperature and pressure and all of that information, calculated instantly for us thanks to the good old brain. Sorry, I talked about that for as long as I could. That was as good as I could do.
Still interesting, though. I like it.
All right.
I like it.
I will
Okay.
be giving the trivia question.
Oh, yeah, let's do it.
Again.
Oh, okay.
Our trivia question today is, who were the first people to use algebra? There's that. And
Okay,
then-
so do we have time for people to call in and guess and answer?
I think I was told we were going to go to break real quick.
Okay, so we do have just a little bit of time, so not much. All right, so are we going to do another question?
Oh.
Or break?
No, we're just going straight to break right now.
Okay, we're going to take a break then. Never mind. And when we get back, we'll answer
And we'll
the
answer the
trivia
question.
question.
There's times when you wander and ponder all the labels you've received.
Believe me, I've got a few. Never mind from when why, or how.
Because now, everything's different. I found the perfect place.
A space where the labels fade and I'm accepted and supported.
Check what the news reported. Emily Griffith helps all who wish to learn.
Turn towards your future while you finish the basics on your time.
Prime opportunity in this mature environment.
The only requirement is motivation and thirst for success.
Invest in your passions. There's no limit to how far you'll go.
And know that you'll have something in common with everyone here.
We all chose empowerment over standing still in fear.
All right, welcome back. Well, I think it's time to answer our trivia question, I believe. Or do we have time for one more question? I don't know.
We're going straight to the trivia question.
All
answer.
right.
So once again, who were the first people to use algebra? And our answer for that is the ancient Egyptians and Babylonians. A little extra information for that. Algebra is a very important thing in today's society. It is used by math by just about everyone from one form or another, but some may ask the question, where did algebra come from? Well, the answer is the ancient Egyptians and Babylonians, and they started using it around 2500 BC. The first type of algebra that was used to solve linear equations and quadratic equations. They used this to solve many equations where many different unknown variables were involved. Ancient Babylonians solved quadratic equations by essentially using the same formulas taught today.
I think this is so cool. Do you think this is cool? I just think this is so cool.
Yeah, of course, the Babylonians and the Egyptians were not calling it algebra, right? Like,
No,
that
not.
is
No.
a modern, and I think, what do you think about this idea that we sort of do a little bit of a disservice to math in general when we like categorize it really strictly like that? Like, I worry that my students sometimes, because I co-teach algebra in some cases, they feel like algebra's here, and then here's geometry. And then here's like way over there is science,
Calculus.
anything to do with science.
right.
Like they're very separate in a way that like algebra is just a word that comes from Arabic, actually.
Yeah.
That was like, it's supposed to be a blanket term for lots and lots of different types of equations, but generally stuff involving variables. Is that a fair way to describe what algebra is?
Yeah, that's definitely how it's described now, as anything involving variables. So there is, algebra involved in geometry and such. But I'm a fan of integrated math, not categorizing it that way and just, this is math.
Well, it's much more natural. I mean, the Babylonians and the Egyptians were definitely doing integrated math.
Yes.
When they were using it.
Because it's all being used.
Right.
And so when you're using it, you need all types of math, of course.
Right.
I think it's really interesting. These cultures, they figured out a lot of the same things, but separately.
Right.
Even though they weren't communicating with each other. They discovered a lot of the mathematical properties that we use.
And actually, I have
today, in their own culture, without sharing or helping each other.
Totally. And there's a math teacher at our school that says often math wasn't invented, it was discovered.
It was discovered.
Because it was there, it is there.
It'll
be there long after we're gone. We have just elucidated some of the pieces.
We've created our own representations for numbers and variables and whatnot. But yeah, exactly. It is. It's just there. It's
the true universal language.
Yes. Speaking of the quadratic equations, the Babylonians are the ones that discovered that. So, because they were talking about area, and I just thought that was really interesting too. But yeah, I don't know. Anything else?
Do you know what algebra means? Well, so algebra comes from the Arabic aljabar. I don't know if I'm pronouncing that right, but it means like the restoration or the completion, and it has to do with the idea of the moving of a piece of a term from one side of the equation to another.
Okay.
That like in the most basic sense, x plus 1 equals 2.
Oh.
X must be 1 or something, or x plus 2 equals 3. X must be 2. Like that piece of completion, that supposedly is what the word is referring to, although it's a little bit unsure. People don't know exactly what the word was there for.
All right. Well, sorry to cut you short, but we do have to say goodbye. We'll see you tomorrow from 4:30 to 5:30. Thanks.